Hi there. So today we're going to continue our work in Chapter 2. We're going to finish Chapter 2 today and start with Section 2.5 on relations. Now, relations is a primitive form of a function. It's the sort of a precursor to a function. It's a primitive mathematical construct, and a relation is just any set of ordered pairs. So in this example, the set of ordered pairs are length of femur and an individual's height. So these ordered pairs, the set of these ordered pairs constitutes a relation. And the domain of the relation is the first elements in the ordered pair, and the range of the relation is the second elements in the ordered pair. So here's another example, and in this example we have a few different states, just 5 different states listed here, and the number of representatives. And this table we can write the list of ordered pairs that define this relation. The list of ordered pairs would be this list. X is the first element in the ordered pair, that's the state, and Y is the second element in the pair, and that's the number of representatives in the state. So the first entry here it corresponds to the ordered pair Alabama 7, and the second entry in the table is California 53, and so on. So here's the 5 ordered pairs that represent this relation. Now we want to identify the domain and range. The domain is the set of first elements in the ordered pair. So the domain in this case is just the states, Alabama through Kansas, and the range is the second item in the ordered pairs. So the range for this example would just be the numbers 7, 53, 25, and 4. Now there's a few different examples. In this example, in both of these, we have to write the relation as a set of ordered pairs and then find the domain and range. So this set represents the domain set, this set represents the range set, and this arrow indicates that 3 gets mapped to -9, 2 gets mapped to -9, and 7 gets mapped to -9. So the ordered pairs would be 3, -9, 2, -9, and 7, -9. So this set of ordered pairs defines the relation. The domain is the set of first elements, so the domain is this set, and the range is the set of second elements. The range is very simple in this case. The range is just -9. Now in the second example, we have a few, looks like 5 different ordered pairs, and these ordered pairs, they're on a grid. Those ordered pairs constitute the relation in this case. So the set of ordered pairs here, well, I put it down here so it would fit better, but this point is the point -2, 3, that's in the relation. This point is the point -1, 0, that's in the relation, and so on. So this set of ordered pairs represents this relation. The domain for this set is the set of first elements in the ordered pairs, so that's the set just of the x coordinates. So -2, -1, 0, 1, and 2. The range is the set of y coordinates, and the y coordinates you can see those are -3, 0, 1, then 0 and -3. But since 0 is already in the set, we don't need to write it a second time. And since 1 is already in the set, it doesn't get written a second time, and so on. So this set is the range. Now we want to do the same exercise with graphs. So this graph, the graph that's represented here, it looks like an ellipse, is a continuous set of ordered pairs. And so the graph, represents the set of all ordered pairs that are indicated here. Okay, now these ordered pairs have x coordinates and y coordinates. So the x coordinates in these ordered pairs, those are in the domain. Okay, And the y coordinates of the ordered pairs, those are in the range. So the domain in this first set, if you take the projection of this object onto the x-axis, so each of these points, they're ordered pairs, and their x-coordinate is on the x-axis. So if you look at that set, it's going to be this set. It's going to be the set from this point all the way to this point. It's this interval of points. Okay, so that interval of points is represented by this closed interval because the endpoints are included. -8 and 8 are points on, are x-coordinates for points on the graph. So this interval from -8 to 8 constitutes the domain. Now, for the range for this set, we're looking to find the set of y-coordinates for this graph. So to get the set of y-coordinates, you're going to project the graph onto the y-axis. So if you project the graph onto the y-axis, you would start down here. That looks like -5. And then this part of the graph in the right half plane, all those points project onto the points that I'm indicating, right? And it goes up to +5. So we're really talking about this interval. That interval constitutes the range. So the range is from -5 to +5. Now for this next object, we're going to do the same exercise. To find the domain here, we're going to project the graph onto the x-axis and see what interval of the real number line is covered. So clearly it starts at 0, the x points, and then if you take the x coordinates, it looks like it's covering the, well, this one stops, right? 4 isn't included, but the top part of the curve, 4 is included. So 4 is in the range, and all the points larger than 4. It looks like it's everything on the positive x-axis. So that point would be from 0 to infinity. And the range, well, it looks like the range would start at -2, but -2 is not included. And then all of these points, if you take the y-coordinate of these points on the graph, the y-coordinate looks like it starts at -2, and then as this continues to increase, the y's coordinates will increase as well. So it looks like the interval we're talking about starts at -2, but then continues. So the range would be from -2 to infinity. Okay, so now we're up to section 2.6, the next section, and we're going to talk about functions. Functions are special types of relations. They're a type of relation where for each element in the domain, there's associated one and only one value in the range. So with that added restriction to a relation, that's how a function is defined. So specifically, if you look at ordered pairs in a relation, such a set of ordered pairs would be a function if no two ordered pairs have the same first coordinate. So here's a bunch of pictures that represent relations, and we're going to determine which of these define y as a function of x. So this set is the x set, domain set, this is the y set, this is the range set, and this first, in part A here, this first example, 1 is associated with 3, 1 is also associated with 4. So if you wrote the ordered pairs in this relation, the ordered pairs would be 1, 3, and 1, 4. Well, this is exactly a case where one element in the domain is associated with 2 elements in the range, and that violates a definition of a function. So because 1 is associated with 3 and 1 is associated with 4, this relation does not represent a function. Okay, now in this case, if we look at B, 1 is mapped to 4, 2 is mapped to -1, 3 is mapped somewhere. Each of the x values are only mapped to one y value. So this does represent a function. And if we look at this last example, 1 is mapped to 4, 2 is mapped to 4, 3 is mapped to 4. each value in the domain, each element in the domain is only mapped to a single value in the range. So this one also, well, here's the ordered pairs. 1 gets mapped to 4, 2 gets mapped to 4, 3 gets mapped to 4, but this is a function because we don't have an element in the domain mapped to 2 different values in the range. So this does represent a function. Okay, so the vertical line test is used as a way to determine if a graph that you're looking at represents the graph of a function. So there's 2 examples here. This looks like an ellipse, and in this case, if we were to draw a vertical line through the graph of this function, if the vertical line intersected the graph in more than one point, then that would mean that that x value is associated with 2 different y values. So that would mean an element in the domain is associated with 2 elements in the range, and that would be a violation of the definition of a function. So if that happened, then the graph we would be looking at, which this one in particular, would not be the graph of a function. So in this case, a vertical line intersects in 2 points, so we conclude this is not the graph of a function. Now in this case, it looks like a parabola actually. If you pass a vertical line through the graph, any vertical line passing through this graph will only intersect the graph 1 time. So that's what we have in this picture. So this passes this vertical line test, and this graph does represent the graph of a function. Okay, so now we're going to talk about evaluating functions. So a function is given here. This looks like g is a linear function. We would read this as g of x. So g of x is equal to 1/2 x minus 1. So it's a linear function because it's an mx plus b. The slope here is 1/2, and the y-intercept is -1. Okay, so we're going to evaluate g for at a few different values of x. So in part A, we'll look at evaluate g at 0. Now g, this is called the x here. Well, x is the variable in this case, and it's called the argument of the function. So really anything that is in this location, what this function g does to it is it multiplies by 1/2 and then subtracts 1. That's what g does. So if we want to evaluate g at 0, what's going to happen is we have to take 0, multiply by 1/2, and subtract 1. Well, this is some simple arithmetic. If we make this evaluation, it would be 0 minus 1, which is just -1. So we can say g of 0 is -1, or equivalently, 0 is mapped to -1, or equivalently, the ordered pair 0, -1 is on the graph of g. Okay, next we'll look at g of 2, and like before, to evaluate g of 2, we're going to multiply by 1/2 and subtract 1, right? So g of 2, we multiply 2 by 1/2 and subtract 1, because that's what the definition of g is. Whatever is in this location, g will multiply by 1/2 and subtract 1. So this is simple to evaluate, and just get 0. So g of 2 is 0. Next is g of 4. So, like before, we'll multiply by 1/2 and subtract 1. So g of 4 will be 1/2 times 4, subtract 1. 1/2 times 4 is 2. So this is going to be 2 minus 1, which is 1. So g of 4 is 1. In other words, 4 gets mapped to 1 under this definition of g. The last case here is g of -2. And like all the other cases, we'll multiply by 1/2 and subtract 1. So g of 2 will be 1/2 times -2, subtract 1. So that's -1 minus 1, or -2. So -2 gets mapped to -2 under g. So now we have a few other, 2 other functions to look at. F is a little more complicated. It's not linear, right? Because we have the 2 up here. So this is a nonlinear function. This is a degree 2 polynomial. but g is a line. G is a linear function. It's an mx plus b. We can see that right here. 3 is the slope and 5 is the intercept. Okay, so in the first case, we just want f of t. So f of t, instead of x being in this location, it will be t. But what does this function do? Whatever is here gets squared, and then from that we'll subtract 2 times whatever was in that location. So in particular, if t is in this location, f of t is going to be t squared minus 2 times t, which is t squared minus 2t. Okay, the next case we're going to look at g evaluated at w plus 4. Now, g is this simple linear function, but in the argument for the function, we're not going to have a single variable now. We're going to have this little expression. And what g will do to this little expression is the same thing g does to anything that's in this location. It's going to multiply by 3 and add 5. So in particular, g of w plus 4 is going to be 3 times w plus 4 plus 5. Because g of whatever is in this location gets multiplied by 3 and you add 5. So in particular, w plus 4 gets multiplied by 3, then we have to add 5. Now to evaluate this is very straightforward. Just use the distributive property and get 3w plus 12, then we add these and get 3w plus 17. So g of w plus 4 is this expression. Okay, last we're looking at f of negative t, and like before, we're going to just substitute negative t in for the argument of the function, and what will happen is we have to square that and subtract 2 times that. So f of negative t will be negative t squared minus 2 times negative t, which is simple to evaluate. That's just going to be t squared plus 2t. Okay, so now we'll look at, oops, I forgot to put animation on that one. Now we'll look at finding function values from a graph. So here's the graph of h. H doesn't look like it's defined everywhere. It looks like the domain here, it starts at positive 5. I mean, well, actually, I should say, I think I misspoke. It ends at 5. It looks like it's defined for all the negative numbers, but then to the positive numbers, it looks like the last, 5 is not included here. That's why there's an open circle. Okay, so what is h of negative 1? Well, negative 1 is here. This is the value for x, the independent variable. So when x is negative 1, y looks like it's 2, right? So this point is the point negative 1, 2. So h of negative 1 is 2, because negative 1 gets mapped to 2 under h. Next, we want to find h of 2. Well, when x is 2, h is 1. So h of 2 is 1. Here's that ordered pair, 2, 1. So 2 gets mapped to 1. So h of 2 is 1. Okay, and h of 5. Well, 5 is here. 5 is not mapped by h. That's why we have this open circle here. So 5 is not in the domain of h. So h of 5 is not defined, okay, because 5 is not in the domain. For what value of x is h of x 3? Okay, well, h of x is equal to 3 here. Only once is h of x ever equal to 3, and that occurs when x is equal to negative 4. So, now it finally comes on. So, h of x is 3 when x is negative 4. Okay, so next, what are we saying here? Okay, so we're going to mention again that the domain for a function is the set of all the x values. It's the It's actually the largest set for which the function is defined. The range is the set of all the y values corresponding to values in the domain. Okay? So when we're thinking about domains of functions, I mean, earlier we did domains of functions because we had ordered pairs or because we had a graph. But sometimes for functions you have a formula. Okay, so for a formula, if you have to find the domain for of the function, then you want to take the largest set where the function is defined. So the largest set, well, you'll start with a set of real numbers, and then you'll have to just take away any points where the function's not defined. So here's the things you have to keep in mind. You have to exclude any values where a fraction would be 0. You know, the denominator of a fraction would be 0. So if your function is a fraction, it has a numerator and it has a denominator. The numerator is the top of the fraction, the denominator is the bottom of the fraction. If the bottom of the fraction is 0, those values of x for which the denominator is 0 are values of x where the function will not be defined. So those values have to be tossed out of the set of real numbers. Those points are not in the domain of the function. The other thing to keep in mind is if you have a function that has a square root. A square root is only defined when what's inside the square root is positive or 0. The square root of 0 is 0, so the square root is actually, it is defined at 0. But it's not defined if the value inside the square root is negative. Those values are called complex values. That's where the letter I comes in. Like the square root of -1, for example, is the letter I. So if you had a function that had square roots, you'd have to exclude values where what's underneath the radical is negative. Okay, so I split up your page here. I know you have A, B, C, and D on this page. I split them up so I could fit everything. We'll look at C and D in the next slide. So here we want to write the domains of these functions. Now this first function is a rational function. This is called rational function because it's a ratio, right? It's a fraction. And we just mentioned that these fractions are only defined if the denominator is not 0, right? So, see this part? This is the denominator, 2x minus 1. And if 2x minus 1 is equal to 0, that happens if 2x is 1 or if x is equal to a half. So at x equal to a half, this function is not defined. So this point, x equal to a half, is not in the domain of the function. So if that point's not in the domain of the function, what's the domain of the function? Well, the domain of the function is going to be all real numbers with that one single point removed. One single point removed. So if that one single point is removed, you have two unbounded intervals that are the domain of the function. This unbounded interval and this unbounded interval. What is this interval? This interval is from -infinity to a half, but a half is not included. And this interval is from 1/2 to infinity. Again, 1/2 is not included. So the domain in this case would be written using interval notation in this way: from -infinity to a half, union 1/2 to infinity. It takes these two unbounded intervals to exclude just a single point. Okay, in part B, we have another rational function. So again, it's a fraction. And again, we have to look at the denominator and think about what points, if any, we'd have to exclude so that the denominator's never 0. Well, in this case, the denominator is x squared plus 9. Well, x squared is always positive, right? If you take a positive number and square it, it's positive. If you take a negative number and square it, it's still positive. And it can't be 0 either because you're adding 9 to the denominator. So the smallest the denominator ever is 9. So this denominator is never 0 and it's never negative. So since that's the case, denominator is never 0, Oh, I said negative, but who cares if it's negative? I said the wrong thing. The denominator is never 0. That's the important point. So the domain here is the set of all real numbers. So to indicate that, we would use the interval from negative infinity to positive infinity. Okay, next we have two other examples. Now in this example we have a radical, and like we mentioned earlier, what's underneath the radical has to be positive in order for this function to be defined. Okay, so we require t plus 4 to be bigger than or equal to 0 in order for k to be defined. So this is a very simple linear inequality, and to solve this, just subtract 4 from both sides. So t has to be larger than or equal to negative 4. So that tells us that this set is the domain of the function. This set is the domain of the function. So we would express that using interval notation as the set from negative 4 to infinity. The last example here is, well, not linear, it's a polynomial of degree 2, and this is not a fraction, so we don't have to worry about the denominator being 0, and it's not a radical, so we don't have to worry about what's underneath the radical being positive. This polynomial is defined everywhere. This has no restrictions. So since it's defined everywhere, the domain for this function is the set of all real numbers. Okay, so that's it. And what you need to do now is get on ALEKS and continue on your path in ALEKS. We finished chapter 2, and when we meet next class, we'll continue our work and we'll begin in chapter 3. Okay? So I'll see you.